right, good morning, everybody. Welcome in. Let's get started. So we kind of finished up one chapter last time, getting into new material today. Yeah. Oh, I got to fix this. This isn't right. That says, hold on, I got to fix something here. I just realized is wrong. This is going to be graded 10 points, not 0 points. Okay, where were we? Okay, so we have a couple more chapters that are really kind of laying groundwork, and then the big kind of, the heavy hitters left are chapters 9 and 10. Those are two concepts that you just have to have and be able to use inside of your project that you're doing. The next couple chapters, 7 and 8, are still groundwork, right? We're still kind of laying the groundwork for some stuff. We've kind of done, there's certain chapters we had, like the probability chapter was really so we could understand later chapters more in depth. So 7 and 8 are kind of giving us some more well-rounded information about statistics so that when we get to 9 and 10, it's going to make more sense to us, okay? So we're looking at that, looking at chapter 7, which is the normal probability distribution, okay? So what does that mean? Well, let's take a look here. We use this word normal in statistics, and it's hard in math because we use words that are everyday words like normal, and we specifically don't use average because that's a word that means something different in the general population rather than statistics, so we don't use that word. So sometimes the words in the English language don't always line up with the exact meanings we have in mathematics. In mathematics and statistics, when we define something, you have to be very careful about how you define it. That's why a lot of times, like, you might read a definition in a book and go, man, why are they making it so complicated? Like, I get what's going on here. It's because further down the road, as you get into more and more complicated problems that you've never considered, and you go, oh, does this fit that definition or not? I'm not sure because the definition is ambiguous. So in mathematics, you're very strict with the definition so that that way when you're talking statistics, everyone knows what we're talking about. We're all on the same page. One of those words is the word normal, right? Normal. So we have this we use the word normal in everyday language to mean, well, it's kind of like, kind of like everything else, kind of like the mainstream, the expected thing, the thing that's not unusual. That's what we mean by normal. In statistics, we mean a very specific thing when we say normal. Okay, now it may have kind of come about because of the English definition, but it means a specific thing. So just kind of be aware of that. When we say the normal distribution, we're not using that in the colloquial English language term. We're using it in the statistics term, right? In fact, I try to never use the other word normal, the colloquial normal, in this class, because then it would get confusing. So anytime you hear the word normal, unless I've just kind of slipped up, I'm using it to mean this capital N, standard normal distribution. That's what we're talking about. So what is that? Well, a lot of our data that we collect comes out in this specific pattern that we call normal. Okay, you have other distributions that we've seen along the way, but this normal distribution has some specific aspects to it. So let's get into a couple of things here. So the focus of this chapter is the concept of normal probability distribution, but we begin with uniform distribution. Some of these concepts, if you can understand and relate the things we're talking to in a uniform distribution, then it's just a little bit of a step further to understand them in the context of a normal distribution, right? So that's why we're kind of comparing the two, to try to take the step all the way to a to a normal distribution, we lose a lot of people along the way. So if we kind of take steps to, it's like think of anything. If it's too high, you can't step up to it, right? So if you put a step in there, maybe that's enough that you can now get to the top. That's what we're doing here with this uniform distribution we're looking at. It's our stepping stone to get to the normal distribution. Uniform distribution allows us to see the following two very important properties. The area under the graph of a probability distribution is equal to 1. So probability distribution is a function that when you can plug in values and it will tell you the probability of that thing occurring. Okay, so you could have a probability distribution, like in my calculus class, there's an example that I always use out of the book, that is the probability of the length of a phone call. So, the phone company takes all the phone calls going through it, and it looks at the lengths, and it does some statistical work, and it figures out, like, the probabilities of how long a phone call is going to be. So you can ask, well, what's the probability that a phone call will last between 4 and 7 minutes? And you can calculate that using a probability distribution, right? So the probability distribution is a function that gives you back the probability of an occurrence. So you can, we could come up with one for dice. What is the probability of me rolling a 3 when I roll a dice? What is the probability of me rolling an odd or a prime? We can calculate all those, but we could put it in the form of a distribution, which would then tell us, we could use it as a function, like the functions you learned about in algebra. The area under the graph in a probability distribution has to equal 1. So that probably makes sense to any of you who have had calculus before. You spend a lot of time talking about the area under a curve. For some of you, that's a very new concept when we graph something and look at the area under it. But that's literally like half of calculus, is calculating the areas under curves. The other is calculating tangent lines. So whether you've taken calculus or not, that's sort of a thing that we look at. So we're actually kind of borrowing a few calculus ideas here. Here's the good news. You don't have to do any calculus in this class, right? We have StatCrunch and computers that are going to do all that for us. You don't have to do the calculus, but there is a little bit of the concepts you're going to want to understand what's going on. So the first is that if a function is giving you the probabilities of an occurrence, then naturally the area under that curve has to add up to 1. Because remember, if you add up the probabilities for the things in your probability space, all the probabilities have to add up to 1. Right? You can't have anything missing. They have to add up to exactly 1. Well, that's represented by the area under the curve. So the area under your curve has to add up to 1. And what's weird is you can have functions that go on forever to the left and right. They don't stop, but your area under the curve can still be 1. Those of you who have taken calculus go, yeah, we understand that. But if you haven't taken calculus, that can seem weird. That you can have an infinite function, but the area under that function would be finite, right? You get into weird stuff in calculus. You get into shapes where has finite volume but infinite surface area, stuff like that. Like weird stuff pops up, the counterintuitive stuff, but that's the way it works. Okay, so the area under the curve, the probability distribution is 1 because that sums up all the possibilities, all the probabilities. There is a correspondence between area and probability, so some probabilities can be found by identifying the corresponding areas in the graph. So that's like where I was telling you, you could graph the phone company's distribution for lengths of phone calls, and if you found the area under the curve from 4 to 7, that would give you the probability of a phone call lasting between 4 and 7 minutes. Okay, so you're just calculating those areas. So we start off with a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So this is why it's easy to calculate. We start with these because it's easy to calculate the area under the curve because they're rectangles, and the area of rectangles is easy to calculate. So what would an example of a uniform distribution be? If I give you a coin and you flip it 10,000 times, those outcomes are going to be pretty close to each other. They're not going to be exactly perfect, but they're going to be pretty close to being, 0.5 for your probability for each of those. If I give you a dice and you roll it 10,000 times, you're going to see that those outcomes come out pretty close. In fact, let's see. Can I do this without... I'll do this without exposing grades. Let me just show you what I'm talking about so you can kind of see here, but I don't want to expose. I don't want to accidentally show something like grades or ID numbers or something like that. So let me do this off screen. I didn't think I was going to use StatCrunch, but I think we should. Back, go there, and then I'll bring in StatCrunch here. We go. This should work fine now. Okay. So, like I said, two uniform distributions, right? If the height of your function is the same, it's a uniform distribution, then the probabilities are all the same beneath those values. So let's take a look at the simulation here for dice rolling. Let's roll a single-sided dice. We're just going to roll one. Compute. All right, so you see in the short term, you run a few, you're getting different values. You don't know what your probabilities are going to add up to, right? But once you do 1,000, see how these probabilities are all about the same? And that's what we would expect. If you're going to roll a dice, you expect a 1/6 chance of getting any of these numbers, right? Now in practice, it never comes out perfect, but that's what you expect to have is a 1/6 probability of getting a 2 or a 1/6 probability of getting a 5. They're all those probabilities are all equal to each other, which means we have a uniform distribution. So your uniform distribution looks like a horizontal line generally, right? Going straight across because they all have the same heights. They all have the same probabilities. Okay, so with that said, let me close that. So that's why you get this kind of a graph right here, right? If this was dice, the height of each of these would be 1/6, right? This is a different problem they did, but a couple things we need for a probability density curve. Darn it, when I put it in a certain spot, it expands to the whole window. I wish Windows didn't do that. I don't know why they do that. Okay, come on. There we go. So the total area under the curve must equal 1. We already talked about that because that accounts for all the probabilities. And then we have this new one. Every point on the curve must have a vertical height that is 0 or greater. That is, the curve cannot fall below the x-axis. So why is that? Why can't we have values down here? Well, that would correspond to a negative probability. What is a negative probability? We already know that a probability has to be a number between 0 and 1, right? And obviously you can't have values greater than 1 because the whole area under the curve is supposed to add up to 1. So how could you have a single point that what would that mean? That would mean the probability of something occurring is 1.2. That doesn't make any sense, right? So we're going to draw this connection between area under the curve and the probability of that thing occurring. So let's take a look. Here we have this is a subway waiting time. Given the uniform distribution, find the probability the randomly selected passenger has a waiting time greater than 2 minutes. So I think the maximum's 5, right? Yeah, so you can't wait more than 5 minutes on the subway because a train comes every 5 minutes. So the subway car, whatever. So you can't wait more than 5 minutes unless you intentionally chose not to get on the train, right? So that means a maximum of 5 minutes. You could get 0 minutes if you happen to be just walking down into the subway at the instant that the doors opened on the train, then you waited 0 minutes, right? So those are extremes. Most people will have waited somewhere between 0 and 5 in the meantime. So they're asking us, find the probability that a randomly selected passenger has a waiting time of has a waiting time greater than 2 minutes. All right, so you would find the area from 2 to 5, and since it has a height of 0.2 and a width of 3, that gives us 0.6. right? So a 0.6 probability, or about 60% of the time, you would expect people to have a waiting time that is 2 minutes or greater. So pretty straightforward to find that area under the curve. All right. Now that you kind of understand that concept, now we're going to get everything messy, right? But again, the messiness will be taken care of the calculus, and the calculus is done by StatCrunch. You don't have to worry about that. Just focus on understanding what I'm talking about, okay? The standard normal distribution is a normal distribution with the parameters mu equals 0 and sigma equals 1. So that is your mean is 0 and your standard deviation is 1. The total area under its density curve is equal to 1. So the total area under here is equal to 1. That's great because that means we can use it as a probability density curve, right? So you might say, well, wait a minute. What if I'm doing something and the mu is not 0 and the standard deviation is not 1, right? The mean's not 0 or the standard deviation's not 1. This is going to fall apart. The good news is we can adjust for that. So don't sweat it. In fact, StatCrunch will do all that work for you as well. You just have to remember to tell it to do that. So imagine, so we've got our z-scores here. These are our standard deviations away, and we might want to figure out the area of certain portions under here. Just like a moment ago, we figured out the area under the curve from 2 to 5, but it was under a rectangle, so it was easy. So right. So you want to start understanding these pictures because they are helpful. So you can do these on software, you can do it on calculator, you can do it on StatCrunch. You make these, basically you've got your area under the curve. The blue area is the part you're trying to measure. So you can have everything that goes up to a certain z-score and stops, and you want to figure out this area. Or you can have it between like an upper and a lower bound, right? So you can calculate that area. All of these pieces of software are going to do that for us. So let's take a look at an example of that. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis, a disease causing bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as a z-score. So if you've ever done this where you go, sometimes you might get a test done for medical reasons, and a lot of times they're measuring like a specific thing where if they're measuring your cholesterol, they're like literally measuring the amount of cholesterol in the bloodstream. But other times you might get back a score and you're like, I don't understand this score. What is this? Well, it's that they've converted everything into statistics so that they can see where you lie. Are you in the 5% of extreme for this kind of particular thing they're looking for? Or like, where do you fall, right? The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1, so that this test was designed intentionally, like they did all the work to shift things around and make sure it had a mean of 0 and a standard deviation of 1. So that way, whatever z-score you get, you can relatively quickly figure out, is that a good or bad score, right? So a randomly selected adult undergoes a bone density test. Find the probability that the result is a reading less than 1.27. Well, so what you would do, you're going to put this in StatCrunch. You're going to get a picture like this. So less than 1.27. That means you go to the z-score of 1.27. The area under the curve would be everything to the left. Now, this is weird for people because you're like, wait, this goes on forever to the left, and the area is still only 0.8980. That's weird for people. How can you have something that goes on infinitely in one direction, but the area is still finite? If you want to know the answer to that question, take calculus, and you'll learn that along the way. So we're not using tables. You'll use StatCrunch for this stuff, but you're going to go in and you'll calculate it, and you'll get back your value. Whoops, did we finish that one? Oh, right. So, yeah, I didn't do the interpretation. So the area here, as you will find by computer, is 0.8980, right? That's that probability. So if you randomly select someone, there's a 0.8980 probability that their z-score will be below 1.27. Why is that important? Maybe this is the cutoff. Maybe the medical examiners have figured out this is the cutoff where you start getting concerned. If your score comes back above 1.27, we need to do further tests. We need to investigate what's going on and look into things a little bit more. But you want to start seeing these pictures and recognizing that the area under the curve is representing a probability. The reason it's so helpful to look at these pictures is sometimes when you read a problem, it's difficult to know, like, how am I supposed to set this problem up? Like, am I looking at a problem I should set up like this, where it's everything to the left? Am I looking at one like this, where it's between two values? I'm not sure. If you can understand the problem and you're used to drawing these pictures, like literally draw yourself a picture and it can help you interpret it, and then that's going to lead you to putting it into the computer, right? Sometimes people just try to jump. Okay, I went through, I read the problem one time, I'm trying to put it in StatCrunch and it's not coming out right. It's probably because you set the problem up incorrectly. You tried to jump right to the actual work. What you want to do is think about it, at least in your head. Some of you will get to where you can do this in your head. Some of you should draw it on a paper where you figure out which version is the one that you're looking for, which of these. And StatCrunch has some flexibility in how it can calculate the different ones, okay? You don't have to worry about this. We don't use tables anymore. We don't want to use them, but also the colleges, they get mad if we use them. All right, and then you get these different pictures, right? So you've got the area to the left of Z. So they've got things on the left. Here you've got values that are in between two values, right? And it is pretty straightforward to put those into StatCrunch. Right. And there's a few different ways you can get into this. Just understand there's a connection between the probability and those areas under the curve. You can also work backwards. You can do problems where, given a known area, can you figure out, like, well, what if we go 25% below the mean and 25% above the mean? That would be the middle 50%, right? And you can get those cutoffs if you want. That's the type of problem you'll be looking at as well. But I don't think we need to get into that. I think that'll be kind of straightforward. Now, this is the kind of thing you're going to start seeing a lot more, that we'll start doing more throughout the rest of the course, is we're pretty good with like 95% is kind of a magic number in statistics, right? If someone says they're 95% sure about them, you're like, okay, that seems pretty sure. So most of the time, that's kind of our default. We want to be 95% confident about things. Now, that's not language that's brought up in this chapter, but it's language that's going to be brought up in a couple of chapters, and it comes right back to this probability type argument right here. So if maybe we want to know the middle 95%, well, if you think about it, it depends on how your problem is set up. Since this one has, I'm trying to see if there's a picture I want to use. I guess it's somewhere else. Right here, if you're trying to find the middle 95%, then the common mistake is people will find this cutoff at 5% here and this cutoff at 5%. But that really means you only have 90% in the middle. So if you have 95% in the middle, that means you have 2.5% over here, 2.5% over here. That's why it's 0.025, because that's 2.5%, 2.5% over here. So just remember, when you're splitting it to get 95% in the middle, that means 2.5% on each side. These are values that are going to come up a lot. You're going to see these z-score values. Like, you're going to keep seeing these come up in examples for the rest of the semester. Because when we want to split things this way with 95% in the middle and 2.5% on each side, these are the z-scores that you're going to use. Those are those cutoff values that you're going to use. So this isn't the first time you're going to see those. Okay? So here's a definition for the standard normal distribution. A critical value is a z-score separating unlikely values from those that are likely to occur. So it's the thing we've been talking about throughout the semester. Once you start getting weird stuff, you want to look at it, right? If you're a doctor and you run a test on 100 of your patients and one of them comes back with a weird test score, you better look at it, right? Maybe that person has something wrong with them and you need to figure out what's going on. Right, and then there's different notations that get used for that. And and you'll get into the details inside of your in those videos, the lessons that you're looking at. So remember, z-score, really easy to calculate. It's just your data value minus your mean over your standard deviation. So we've got the standard normal distribution is that one where you've got a mean of 0 and a standard deviation of 1. But most of the time in real life, you're not going to have that. So you can either convert everything to the standard model, or you can, the easier thing to do is just calculate it with the new values. Let me find where that is. These problems are pretty straightforward, I think, from the videos. So remember, we keep seeing it here, and I mentioned it earlier in the class, but a normal distribution has to be roughly symmetric and roughly bell-shaped. Okay, so if it's not bell-shaped, it's not a normal distribution. If it's not symmetric, it's not a normal distribution. Now, nothing's perfect in real life. When you're collecting massive data sets, you never get something that's exactly symmetric where it folds over on itself identically. But you can do pretty good. If you fold it over on itself and it's pretty close, then you go, okay, yeah, that's bell-shaped and symmetric. Many of the tools that we use in statistics are, they still work if your function is not exactly normal, but it's pretty close. Then normally these tools are still going to be good enough to use. We do have, off the top of my head, I forget if it's 1 or 2. I know there's 1. There might be 2 things that we do, I forget, where we have to be a little stricter with our understanding of a normal distribution. And if something isn't normal, then we can't use that tool. But that kind of comes around at the end. Okay. And they have a couple hints here. Don't confuse z-scores and areas. Students get confused about that. Let's look at the graph again, and you'll start to understand. So the z-score is like your x value, right? It's the thing that's on your x-axis here. That's marking where you're measuring. The area is the actual pink area. So, but I'll see students do that where they get this and they're like, that's my z-score. No, the z-score is how you got here. The z-score is like on your axis indicating where you start and finish. The area is like the color that you're shading in on the graph as your area under the curve. Okay. Right. So. Right. We'll get to one of those. We'll do one of those. We'll look at that depending on how time goes for this. Right. Okay. Oh, I should grab that book. Where did my book go? Let's see. Thought there was something I wanted to do next. Do I self-stack crunch open? Okay, good. I want to double check something. All right, sorry, there was something I wanted to talk about, but I can't find the problem I wanted to discuss. So let's move ahead. And again, I'm kind of doing like the 30,000 foot view to fill in the overall idea. The basics I think you'll get from looking at the from looking at the lessons, the lessons that you're watching and getting points for. So here's kind of a basic, let's see, what do we have, 18 minutes? Yeah, that should be good. Here's kind of an idea that you want to start getting the sense of, and why does this normal distribution come about? Like, why does this occur? Like, why is this a shape that we see again and again and again in statistics, right? And it's just, it captures a certain behavior of something that happens a lot. So let's kind of do a thought experiment for a second. So let's say we're sitting in a classroom, or even, I guess, social distance, and every one of you has a coin in front of you, like a fair coin. We all have the identical coin in front of us, and we all say we're going to go through and we're going to flip that coin 100 times, and we're going to keep track of how many are tails. Okay, we actually do, when I have more time and we're in the classroom, we do an experiment similar to this with people sampling pennies that are drawn from a bag and trying to figure out how many types of a certain type are in there. You can actually use this to make predictions, but I'm just giving you an example here so you can understand how this works. So you all have a coin in front of you, and you all start flipping the coin, and every time you get heads, you put a tally mark. Every time you get tails, you put a tally mark. Okay? So we know that the true probability of a coin like that is 0.5, right? So that's already known to us. Well, that means that if you flip a coin 100 times, you're kind of expecting to get 50 heads and 50 tails, right? But are you going to get 50 heads and 50 tails? And the answer is probably not. It's actually more likely that you won't get 50 heads and get 50 tails than that it is, but you probably will be close, right? The further away you get from that, the less likely we are to see that. So, for instance, are we going to expect that if every one of us flips a coin 100 times, how many of us do we think are going to get 100 tails? Like 0. No one thinks that, right? That would be so extreme and so unlikely that it isn't going to work. So, but what if I had everyone give me their number? How many tails did you get out of 100 coin flips? And you gave me your numbers, and we started graphing them. What you would see is a shape like this, because you're going to see a lot of numbers right around 50 tails. Some people are going to have 51 tails. Some people are going to have 49. Some people with 48 tails. Some people with 52. But the further away we get from that 50 tails, the numbers are going to drop off. And it's not going to be perfectly symmetric. It's not going to be perfectly bell-shaped. But we would expect to see something like this, right? And it kind of makes sense. You're targeting, the target is 50 tails. So the more times we do it, like what we talked about before with the law of large numbers was repeating one experiment a large number of times. What we're talking about here is repeating the experiment a large number of times. So it's a little bit different. Each of you would come back, but none of you would believe your value completely, right? If you said you predicted that you flipped a coin and it was going to come up, you say, okay, I'm going to flip this 100 times. I'm expecting to hit about 50 heads and about 50 tails. Let's say you did that experiment and you got 60 tails. Are you going to assume that you have a special coin that comes up tails 60% of the time? Probably not. You're going to assume that, well, I'm kind of over here where I got one of those extreme values. We still think it should be 50-50, but my measurement is kind of over here on the edge. So that's a problem with doing the experiment once, is you have one value and you're like, well, it doesn't meet what we thought it was going to do, but it's not super unusual. It's not super weird. It's not like getting 100 tails. But if everyone in the class did it, we would see the values bunch up like this, and we'd go, oh, yeah, the true value is kind of right here in the middle. So even though we're getting variation between our measurements, if we take enough measurements, then we can see what the actual value is. And in statistics, we can do that, right? And physics has weird stuff too, where they use statistical measurements like this to measure things that are really bizarre. And they'll measure things a bunch of times and then graph it and see where that middle of that thing falls. So like the experiment that I do in class that we're not going to go over, I have a bag full of 2 different types of pennies, right? So some of you may have seen these. They have the old actually, it's not the wheat pennies I use. It's the one with the shield on it or whatever. And then your traditional penny where it's got the Lincoln Memorial on the back. So there's two different types of pennies, but you don't know the percentage of pennies that are in the bag, right? So there's I think I had, I don't know, some large number of pennies, 100 pennies or something like that in a bag. And I don't even remember the numbers, but they're not equal. They're not half Lincoln Memorial pennies and half shield pennies, right? There's some smaller number of shield pennies. Well, of course, we could take them all out and count them, but in real life, you can't always do that, right? If we could count everything perfectly all the time, we wouldn't need statistics. So what we do in my class when we're running this experiment is I've got this black bag with some pennies in it, and every person comes up one at a time, and they grab, I forget how I have the thing set up, but they grab, say, maybe 25 pennies. I think it's 20. Maybe it's 10 or 20, somewhere around in there. They pick 20 pennies, and they put them down, and they measure how many of the shield pennies they got, and then we mark it on the board in a list like this. So the first student would tell me how many they got. Okay, that's your X1 bar. Next person comes up. So what are we doing? We're random sampling. Each person that comes up is random sampling the pennies from the bag. Okay, so each one's a random sample, and then each one gives me a different measurement. Sample 1, sample 2, sample 3. So we have this unknown value we're trying to figure out, but then when we graph those values, we see this. We see a normal distribution where you can tell where the numbers are piling up. Well, generally, by the time we finish it, it's usually really close to the actual value. In fact, I think only once we haven't hit the number right on where it tells, one time we were off by 1 penny or something. But it's really close to telling you, for instance, all these means are, if you look at the X value right here, what's in the middle? So it'll be 30, meaning 30 shield pennies. Some people got, some people estimated that there was a few more. Some people estimated a few less. But we can see right where that is, and then we can... Actually, if you only did 20, it would be this would be right around 6 or 7, but then you would multiply by 5 to see how many you think are in the full bag, the empty bag. So right where this is, that can give us some unknown information that allows us to make predictions. And it's always gone really well in the classroom. It works really good. So hopefully that makes sense. I know this is kind of a complicated idea, but it just means if, think of it in that simplest terms. If we were all flipping a coin, we're not all going to get 50 heads and get 50 tails, but we're kind of sort of be in that neighborhood, and we'd get a distribution like this where the middle's right at 50 tails. Okay. You can get skewed behavior, of course, right? We have very skewed behavior. If we were to sample the ages of students on campus, we would get very skewed behavior because there's a lot of 18 and 19-year-old students on campus. There's a lot less 17-year-old students. So you would see it very, very cut off on one side, and yet there's no strong cutoff on the other side, right? The numbers go down, but, it's not unusual to see a 20-year-old on campus. It's not unusual to see a 21 or 22-year-old on campus. I went to community college for 4 years. I was walking around campus at 22. And then a lot of people that are still working on stuff in their 20s, some people 30s, 40s. So you see this kind of long tail behavior. Okay, but this is not a normal distribution right here. This is. So for means, we can find the means of things by calculating a normal distribution. That is, we keep sampling. We throw the samples into it gets kind of meta, right? Where we have a population that we're trying to measure, so we sample it, but we sample it a bunch of times, and all those samples become our new form of data. Can you see how it's kind of an inception? We've got levels of data. We've got our original data that we're sampling, but then we start sampling our samples is what we're doing here. And as a shape emerges, it starts to give us some information that we're looking for. We can do the same thing with proportions. So remember, a mean is what the mean is. You can calculate a mean, and a proportion is like what percentage of students support a tobacco ban or whatever. We can do that same thing with proportions. If each of you went out and asked 100 people on campus if they support the full tobacco ban, you each would come back with one of these little P1s, P2, P3s. We could get meta and create a new set of data that consists of your sample proportions, and by doing that, we would probably get something like this, where, just theoretically, I don't remember what the values are, theoretically say that 80% of students support a full tobacco ban. Well, then this height you'd expect to be right around 80 right here. Some of you, when you ask people, you would have calculated 83%. Some of you 75%. But we're going to see it pile up right around the true proportion. Okay. So really, in my opinion, this concept I'm trying to get at is really summed up by this picture here and this picture here, and just kind of understanding we're incepting things a little bit. We're taking sample data of our sample data, right? We're creating a bunch of samples, and then we're using that as a new form of data. All right, our definition here. The sampling distribution of a statistic is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population, right? So we could do that on campus. We've got, 10,000 students approximately at VC, somewhere in that neighborhood. It varies from year to year. 10,000 students. Well, we're not going to get feedback from 10,000 students, but I could send each of you out to ask 100 students and just say, hey, in the next week, talk to 100 of your fellow students and ask them if they support the tobacco ban. And each of you would come back with a value. Now, notice it says of the same size n. So that means each one of you have to do the same sample size, 100. Otherwise, the numbers don't come out right. Okay, but I send each of you out, go ask 100 people. You come back. You're all asking the same population, VC students. And then we can look at what that means. What do we got? About a few minutes left. Right. I think that's makes sense. Right. So this is just kind of a more specific version of what we looked at. You go out, you're all measuring sampling procedure, roll a die 5 times and find the mean X bar, right? So you each roll a dice 5 times, you add up those numbers, find the mean. Some of you are going to come to me with 3.4, some of you with 2.8, some of you with 4.4. But what we would see is this overall data. Now, this was the reason that I was making this and also some other work that we'll be doing. I was really trying to push lots of people to take that survey. This is the class where I think more people took it. My other class, my late start class, it's like half the people took the survey, and they're going to be in trouble because when you go to graph something, the smaller your n is, this shape gets harder and harder to read. It gets harder and harder to see. Is that normal or not? It's hard to tell because when n is so small, it just looks kind of dented and messed up. Like when I do those simulations, in StatCrunch, and when I do 1,000 at a time, that shape really starts to take form, right? But in the early days, you can't tell what the shape is at all. That's why we really needed everyone taking the survey. And same thing here with our proportions. See how it's kind of blocky and hard to read? Doing that. So here's a way of saying what I'm trying to get at. The sample means target the value of the population mean, right? It's kind of like a dartboard, and we're all, say you're playing a game where you're trying to hit the bullseye. Well, let's say it's a brand new board, right? Never had anything thrown at it. And you have a bunch of people trying to hit the bullseye. Well, some people are going to hit the bullseye. But what you're going to see is the closer to the bullseye you get, there's going to be more holes in that dartboard because people were going for that spot. And when they miss by a little bit. You're not going to see a ton of holes out by the numbers, right? Assuming we're talking about people who at least somewhat know what they're doing with darts. You're not going to see a lot of holes out by the numbers. They're going to be, the closer you get to the bullseye, you're going to see more holes. That's basically what this is saying, is that the sample means may not exactly hit the true mean of the population, but they're targeting it. They're getting close to it. They're going to be in the vicinity, Okay. And the distribution of sample means tends to be a normal distribution. Now, this is weird because remember, we've got two layers going on here, this sort of inception. We've got the original thing we were measuring and our samples, and then we've got like our set of samples, right? So this is where we're getting meta with it. We're taking the samples you all measured, and we're applying statistics not to the original data. We're applying statistics to your sampling data. That sampling data will generally be a normal distribution, even if your original data was not a normal distribution. So, for example, I've talked about how the ages of students on campus is not a normal distribution. It is very skewed. Right at 18, 19, you see really high values, and then they start to kind of slowly level off as you increase in age, but they cut off pretty sharply at 17. 17 and below, you get a few people in those age groups, but very, very few. So that would not be a normal distribution. It would definitely be skewed. But if I sent you all out and each of you asked 100 people their age of VC students, and you came back and we plotted that data would be normal, which is huge because a lot of the tools we have in this class require you to use normal data. That's capital N normal, like what we mean in statistics, normal. So that's good that if we're dealing with something that isn't normal, we can still do some work and use some of those tools that involve normal behavior. Don't worry about the formulas. We won't need to use those. Right. I think that's where we want to leave off. So I'll talk next time about estimators and unbiased estimators. We'll talk about that a little bit, and then we can expand on the stuff we've done. And I'll do some examples for you in StatCrunch, so you can actually see this stuff at work. We'll use look at some of those pictures where you had like you were figuring out the area under the curve and trying to calculate a probability from that. I'll show you how to do that in StatCrunch. You can find it in the meantime by just looking for a video on YouTube. But I'll go over that, and then we'll pick up with this estimator, unbiased estimator stuff as well. So today's Tuesday. I do have office hours until 10 today. As always, you can just stick around and ask me questions about class if you have any. But keep up the good work as far as those of you who are doing good with the homework and staying on track here. I know this is the time of year people start getting really tired. I get it. And then also you have this disruption of some holidays that are coming up, and it kind of throws people off a schedule, and it can be it's hard for students. I get it. It's hard to come back from Thanksgiving where you had a day off and there was a big family get together and maybe you didn't have to work, and it's hard to come back and just dive right into all that hard work again. But, finish strong and hopefully end up doing well. So come into Zoom, ask me questions that you need. Otherwise, I'll see you in a couple days. All right, thanks, everybody.